In barely a day and a half, a storm most people had never heard of exploded from a sloppy tropical system into a Category 4 monster with winds near 125 knots. Its name is Mekkhala, and on June 22nd, 2026, it became the most violent storm the planet has produced this year. But here's the part that should chill you, and it is not the wind. It is the speed. Storms are not supposed to be able to do this, not this fast, and not in June. Stay with me to the very end, because what made Mekkhala detonate is quietly changing in every ocean on Earth, and the warning it carries is meant for you. If a storm that explodes this fast unsettles you, subscribe so you do not miss what the ocean does next. Drop a comment telling me where you are watching from, and whether a storm has ever caught your town off guard. Now, let us get into it. Somewhere east of the Philippines, over a patch of ocean most people will never see, a storm did something this week that should make all of us pay attention. In the span of barely a day and a half, it went from a sloppy, disorganized tropical storm into a Category 4 monster with winds near 125 knots. That is roughly 230 kilometers per hour, or about 143 miles per hour, wrapped around an eye of dead calm with a central pressure measured near 937 hectopascals. Its name is Mekkhala, and for a few hours on June 22nd, 2026, it became the most violent storm the planet has produced so far this year. Here is the part that should unsettle you, and it is not the wind speed, it is the clock. Storms like this are supposed to take their time. They are supposed to spin up over days, giving forecasters and coastlines and emergency planners a chance to think, to warn, to move. Mekkhala did not do that. It strengthened by about 50 knots in 24 hours and by roughly 70 knots over 36 hours. To put that in plain terms, a storm that looked manageable one evening was a screaming Category 4 the next. That gap between what people expected and what actually arrived is exactly where disasters are born. You have probably heard the phrase rapid intensification before, usually in the same breath as a hurricane that blew up just before landfall and caught everyone off guard. What you may not realize is that meteorologists have an actual number for it. Rapid intensification is officially defined as a storm gaining at least 30 knots of wind in 24 hours. Mekkhala did not just cross that line, it nearly doubled it. And it did so in June, weeks before the Western Pacific is supposed to be capable of producing something this strong. There is a reason that timing matters, and we are going to get to it, because it is the real story hiding underneath the headlines. This is not just a video about one powerful storm spinning harmlessly over open water. It is a video about speed. It is about how fast the ocean can now turn a flicker into a furnace, and about what happens to all of us when the warning time we have always relied on quietly starts to disappear. By the time you reach the end of this, you will understand exactly how Mekkhala exploded, why it happened a full season early, where it is heading next, and why a growing number of scientists believe that storms like this are no longer the exception. They are becoming the rule. So let me show you how a monster is built. And let me start at the very beginning with a single unremarkable cluster of thunderstorms that almost nobody noticed. To grasp what 125 knots actually means, set the number aside for a moment and picture the force itself. Winds at that speed do not simply blow. They peel roofs off their joists, drive splinters of wood through walls, turn loose objects into projectiles, and pile the ocean into a surge that can swallow a coastline. A Category 4 storm is not a bad weather day. It is a regional emergency wearing the shape of a spiral, and the people who study these systems for a living do not reach for that label lightly. Now lay the timing back on top of that picture, because the timing is what makes Mekkhala remarkable rather than merely powerful. A coastline can prepare for a Category 4 if it watches the storm approach for days. What it struggles to survive is a Category 4 that was a tropical storm the day before. The defining feature of this system was never just its peak strength. It was the speed at which that strength appeared, and that speed is the thread that will run through everything we are about to examine. Consider how a forecast works in practice. Emergency managers do not act on the storm in front of them, so much as on the storm the models say is coming. They stage supplies, call evacuations, and position rescue crews based on a predicted intensity and a predicted track, and all of that planning assumes a certain pace of change. When a storm holds to that pace, the system works. When a storm sprints, the plans built around a slower timeline begin to fall behind reality, and the people relying on those plans can be caught in the gap. That gap is the quiet danger at the center of this entire story, and Mekkhala widened it about as far as a storm can. So before we talk about where it went and who it threatened, we have to understand how it grew so strong, so fast. And to do that, we have to go back to the moment it was nothing more than a flicker over warm water. A flicker that almost no one thought twice about. Every monster starts small, and this one started as little more than a smudge on a satellite image. On June 18th, 2026, a loose area of thunderstorms gathered over the warm water to the east and slightly south of Guam. There was nothing dramatic about it. The tropical Pacific produces these disturbances constantly, and the great majority of them fizzle out within a day or two, torn apart by dry air or unfavorable winds before they ever organize. This one did not fizzle. It found exactly the environment it needed, and it began to turn. The system organized quickly enough that by June 20th, it had crossed into what the Philippines calls its area of responsibility, the zone of ocean the National Weather Agency watches like a hawk, because anything that forms there can threaten the islands within days. When a storm enters that zone, the Philippine agency gives it a local name, and this one was christened Francisco. Internationally, though, it already carried another name, drawn from a list maintained across the Western Pacific. That name was Mekkhala, a word borrowed from Thai mythology for the goddess of lightning. The forecasters at the United States Joint Typhoon Warning Center, who track every storm in the basin, simply labeled it Tropical Cyclone 07W. So already we have one storm wearing 3 different names, and that is worth pausing on, because it is going to matter later when we talk about why people accuse the authorities of hiding things. A storm named Francisco by one agency, Mekkhala by another, and 07W by a third is not a conspiracy. It is just the messy, overlapping reality of how the world tracks weather across borders and oceans. Hold on to that, because we will come back to it. For now, what matters is what the young storm was sitting on top of. The ocean beneath Mekkhala was extraordinarily warm, with sea surface temperatures running around 29 to 30 degrees Celsius. Warm water is fuel for a tropical cyclone, and water that warm is high octane. But warm water alone is not enough. Plenty of storms sit over hot oceans and still fall apart, because something up above shears them to pieces. The killer of tropical systems is wind shear, the change in wind speed and direction with height, which can decapitate a storm by blowing the top of it in a different direction from the bottom. Mekkhala had almost none of that working against it. The vertical wind shear over the storm was low to moderate, somewhere around 15 to 20 knots, gentle enough to let the system stack itself neatly into a vertical column. And high above the storm, the air was flowing outward efficiently, what forecasters call robust radial outflow, which acts like a chimney venting exhaust away from a fire, so the fire can keep burning hotter. Warm ocean below, light winds aloft, an open chimney up top. If you wanted to design the perfect laboratory conditions for a tropical cyclone to detonate, this was close to it. And detonate is the right word, because what happened next was not a slow build. It was an explosion in slow motion, captured frame by frame from space. The storm that entered June 22nd as a strengthening but ordinary system would, within hours, becomes something that belongs in the record books. To understand just how violent that transformation was, you have to understand what is actually happening inside a storm when it goes through rapid intensification, and that is where the physics gets genuinely frightening. There is a detail in that favorable environment worth slowing down on, because it explains why this storm did not just strengthen, but accelerated. The warmth feeding Mekkhala was not a thin skin of hot water lying on top of a cold ocean. It ran beneath the surface, a thick layer of heat that oceanographers measure as ocean heat content. That distinction matters enormously. A storm constantly churns the sea below it, dragging up water from underneath, and if that lower water is cold, it acts as a brake, cooling the surface and starving the engine. When the warmth extends well down, there is no brake. The storm keeps pulling up fuel no matter how hard it churns. That is the difference between a storm that strengthens steadily and one that detonates, and Mekkhala had the second kind of ocean underneath it. Combine a thick reservoir of heat with the light wind shear and the open chimney of outflow aloft, and you have removed nearly every obstacle that normally keeps a tropical cyclone in check. The system was not fighting its environment. Its environment was actively helping it on every front at once. It is also worth remembering where on the calendar this was happening. The Western Pacific typhoon season runs all year in a technical sense, but its violent peak normally arrives later, from August through October, when the ocean has soaked up a full summer of sunlight and its stored heat is at the yearly maximum. For the sea to be this primed in June is itself a sign that the ocean is running ahead of its own schedule, and that early loading is part of why Mekkhala could do what it did when it did. So the stage was set by an ocean that was too warm, too early, with nothing in the sky to stop what was coming. The flicker off Guam had found a perfect machine waiting to be switched on. And once it switched on, the transformation that followed was so fast and so complete that to truly appreciate it, you have to understand the physics turning inside the eye. The engine that converts warm water into one of the most destructive forces on the planet. A tropical cyclone is, at its core, a heat engine, and that is not a metaphor. It is a machine that converts the warmth stored in ocean water into the kinetic energy of wind, and like any engine, its output depends on its fuel and on how efficiently it can run. The fuel is the warm sea, specifically the heat held not just at the surface, but in the layers of water beneath it, what oceanographers call ocean heat content. The more deeply that warmth extends, the longer a storm can keep feeding, because as it churns the sea, it keeps pulling up more warm water instead of dredging up a cold layer that would starve it. When a storm taps into a reservoir of heat like that, with nothing tearing at it from above, the process can become self-reinforcing in a way that turns terrifying very fast. Warm, moist air rises in the storm's core. As it rises and cools, the water vapor in it condenses, and condensation releases heat, which warms the surrounding air and makes it rise faster still. That falling pressure at the center pulls in more air across the sea surface, which picks up more moisture, which rises and releases more heat. Round and round it goes, each turn of the cycle feeding the next, the winds accelerating, the pressure dropping, the whole system tightening, like a figure skater pulling in her arms and spinning faster. That feedback loop is what we are really describing when we say rapid intensification, and Mekkhala rode it about as hard as a storm can. Remember the official threshold, an increase of at least 30 knots of wind in a single 24-hour period. Mekkhala gained roughly 50 knots in that window, and about 70 knots across 36 hours. By the time it peaked, it was carrying sustained winds near 125 knots, with a central pressure around 937 hectopascals, and it had briefly clawed its way to the threshold the Joint Typhoon Warning Center uses to call something a super typhoon, which is 130 knots. On the scale most people know, the Saffir-Simpson scale, those winds put it firmly into Category 4 territory, the range that runs from 130 to 156 miles per hour. There is one more piece of internal machinery worth understanding, because it explains why these storms can be so maddeningly hard to forecast. The most intense tropical cyclones often go through something called an eye wall replacement cycle. The eye wall is the ring of towering thunderstorms surrounding the calm eye, and it is where the strongest winds live. In a very powerful storm, a second ring of thunderstorms can form farther out and slowly strangle the inner ring, cutting off its supply of warm air. The storm temporarily weakens as the inner eye wall collapses. Then it can reorganize around the new outer ring, sometimes ending up larger and capable of strengthening all over again. These cycles make a storm's intensity wobble in ways that are genuinely difficult to predict from one forecast to the next. So when you see a storm's strength jump and dip and jump again, you are not watching the forecasters get it wrong. You are watching a chaotic, living system fight with itself in real time. And here's the question that should be forming in your mind right now. If the fuel for all of this is warm ocean water, and the ocean is getting warmer, then what does that mean for how often storms can do what Mekkhala just did? That question takes us out of this one storm and into something much larger and much harder to look away from. There is a useful way to picture rapid intensification, borrowed from the world of fire. Firefighters talk about flashover, the moment when a smoldering room crosses a threshold and everything that can burn ignites almost at once, turning a manageable fire into a lethal one in seconds. Rapid intensification is the tropical cyclone version of that moment. For hours, the storm builds quietly, and then it crosses a line where the feedback loop takes over, and the intensification that follows is not gradual. It is a cascade, each part of the system driving the next harder and faster. What makes that cascade so difficult for forecasters is that the threshold is hard to see in advance, and the eye wall replacement cycles we just described add another layer of unpredictability on top. A storm can be strengthening, pause as an inner eye wall collapses, then surge again as a new one organizes, and each of those swings unfolds over just hours. The models that forecasters rely on have improved dramatically at predicting where a storm will go. Predicting exactly how strong it will be, and exactly when, remains one of the hardest problems in the science, precisely because of cascades like this. That difficulty is not a failing of the forecasters. It is a description of how genuinely chaotic these systems are. A tropical cyclone is a churning, living thing fighting with itself, balanced between the fuel feeding it and the forces trying to tear it apart. And small changes in that balance can produce large changes in the outcome. When a storm like Mekkhala tips decisively toward the fuel, the result is the kind of explosive growth that compresses a multi-day strengthening process into a day and a half. And that compression is the whole problem, brought back into focus. Every hour that a storm shaves off its intensification timeline is an hour stolen from the people in its path. So the question stops being academic and becomes urgent. If warm water is the fuel that powers these cascades, and the world's oceans are steadily warming, are we building a future in which the cascade becomes the norm rather than the exception? The answer, unfortunately, is already taking shape in the data. For a long time, rapid intensification was treated as a kind of meteorological wildcard, something that happened occasionally and dramatically, but unpredictably. Over the past decade, though, the science has shifted, and the picture that has come into focus is not comforting. A growing body of peer-reviewed research has found that the proportion of storms undergoing rapid intensification has been increasing, and that the fastest intensification rates, the most extreme jumps, are trending upward over time. In other words, what used to be the wild card is being dealt more and more often. The reason is not mysterious, and you already understand the mechanism, because we just walked through it. If a tropical cyclone is a heat engine running on warm water, then warming the water turns up the maximum power the engine can reach. A hotter ocean does two things at once. It raises the ceiling on how strong a storm can ultimately become, and it removes one of the natural brakes that used to slow intensification down, because the warmth now extends deeper, so a churning storm no longer reaches a cold layer that would have choked it. The dice have not changed in number. The faces have been re-weighted toward the high end. Mekkhala is almost a textbook illustration of this. It blew up over water near 30 degrees Celsius in the month of June, weeks ahead of when the Western Pacific is traditionally at its most dangerous. And the result of that early season heat was a storm that earned a specific and sobering distinction. It became the strongest typhoon to form in the month of June in 22 years, the most violent June storm the basin has produced since 2004. When a record like that falls, it is tempting to file it away as a curiosity, a piece of trivia. But records are how we measure a moving baseline, and a June record for raw intensity is exactly the kind of signal climate scientists have been warning we would start to see. Now, it is important to be honest here, because intellectual honesty is the whole point of doing this carefully. No single storm can be blamed on a warming climate the way you might blame a broken window on the rock that went through it. Weather is chaotic, and a powerful storm has formed in June, before, and will again. What climate science actually says is more subtle, and frankly, more disturbing than a simple cause and effect. It says that as the oceans warm, the odds shift. We are not necessarily going to get more storms overall. We are going to get a higher ceiling, a faster on-ramp, and more storms that sprint from harmless to catastrophic in the time it takes to reweigh a forecast. Think about what that does to the one thing coastal communities depend on more than anything else, which is time. Every evacuation, every boarded window, every decision to leave or to shelter depends on having enough warning. The entire system of preparation assumes that a storm gives you a reasonable runway between the moment it becomes dangerous and the moment it arrives. Rapid intensification eats that runway. When a storm can gain 50 knots in a day, the comfortable lead time that planners assumed they had can evaporate overnight, sometimes literally overnight, while people are asleep. That is the quiet horror underneath Mekkhala, and it has nothing to do with secret weapons or hidden agendas. It is simpler and more permanent than any of that. We are, through ordinary everyday emissions, slowly loading the dice toward faster and stronger storms. And we are doing it out in the open, in full view, measured and documented and published. The storm itself will weaken and vanish into the North Pacific within days. The trend it represents is not going anywhere. And to see why that trend has teeth, you only have to follow Mekkhala's path and look at who is standing in the way. It helps to put a name to the kind of ocean condition that feeds storms like this, because it is showing up more and more. Scientists increasingly talk about marine heat waves, prolonged stretches in which a region of ocean runs far hotter than normal, and these events have become more frequent and more intense as the planet has warmed. A storm that wanders over a marine heat wave finds an almost bottomless tank of fuel, and that is exactly the kind of setup that turns an ordinary system into a rapid intensifier. The warm water near 30 degrees Celsius that Mekkhala fed on was not an accident of 1 week's weather. It is part of a longer warming signal in the sea. The honest scientific framing here is about probability, not certainty, and that distinction is worth defending because it is where a lot of public confusion lives. No one can run the experiment of a world without warming to see whether this specific storm would have formed. What researchers can do is measure how the odds have shifted, and the measured shift is consistent and in one direction. More of the fastest intensifiers, higher ceilings on peak strength, a bigger share of storms making the leap that Mekkhala made. The individual storm is weather. The trend across thousands of storms is climate, and the trend has teeth. You can think of it as the difference between a single roll of the dice and the design of the dice themselves. Any one storm is a roll, and rolls are unpredictable. But if you quietly add weight to the side that says faster and stronger, then over enough rolls, the outcome is not in doubt. You will see more violent results. More often, even though you can never point to one roll and say the weighting caused it. That is precisely the relationship between a warming ocean and a storm like Mekkhala. And the consequence of that re-weighting lands hardest on the one resource no coastal community can manufacture, which is time. We have built our entire relationship with these storms around the assumption of a reasonable warning window. Rapid intensification attacks that assumption directly. So to see what is actually at stake, we have to stop talking about Mekkhala as a number on a scale and start following it as a moving threat across an ocean lined with people who had to decide in a shrinking window what to do. A storm's strength only becomes a story about people when you trace where its energy actually goes, and Mekkhala's track is a tour of some of the most populated and strategically important real estate in the Pacific. The first to feel it were the Philippines, even without a direct hit. As Mekkhala churned through the waters east of the islands, it dragged the southwest monsoon, known locally as the Habagat, across the southern part of the country, wringing out heavy rain over Mindanao. The result was a large-scale displacement event. According to the Philippine National Disaster Risk Reduction and Management Council, 85,295 people were forced from their homes in the Bangsamoro Autonomous Region in Muslim Mindanao, with infrastructure damage reported on the order of 3.4 million pesos. Sit with that number for a moment, because it is easy to skim past. More than 85,000 people displaced, and the storm never even made landfall there. It simply passed close enough and pulled in enough tropical moisture to overwhelm communities from a distance. That is a reminder that a tropical cyclone is not just its eye and its eye wall. It is a sprawling engine that can reach out hundreds of kilometers and reshape lives in places it never directly touches. From there, the steering currents took over. Mekkhala was being guided by a subtropical ridge, a sprawling dome of high pressure sitting to its northeast, and storms travel along the edge of these ridges like a marble rolling around the rim of a bowl. That track carried Mekkhala west, northwest at first, then bent it northward, and then began to swing it toward the northeast. The next target along that arc was Okinawa, the Japanese island that is home to a dense civilian population and to major United States military installations. Forecasters projected the closest approach to Kadena Air Base to come around 1 a.m, Coordinated Universal Time, on June 26th, with the center of the storm tracking right along the northwest coast of the island. Japan's meteorological agency issued warnings, and ports across Okinawa prepared for closure as the storm bore down. After Okinawa, the forecast called for Mekkhala to accelerate, racing northeastward and skirting the southeastern coast of Japan's main island of Honshu, passing just to the south of Tokyo. And here we have to talk about a transformation that often gets overlooked, because it changes the nature of the threat entirely. As a tropical storm moves into the colder waters and stronger high-altitude winds of the middle latitudes, it can undergo what is called extratropical transition. The storm merges with the weather systems of the temperate zone and reorganizes into something different, often a very large, sprawling system, driven less by a warm tropical core and more by the clash of air masses. The danger of that transition is that a storm can actually grow in size, even as its tropical core decays, spreading damaging winds and heavy rain across a much wider area than its peak intensity footprint ever covered. So the threat to the region around Tokyo, the most densely populated metropolitan area on the entire planet, was not necessarily a screaming Category 4 eye wall. It was the broad, soaking, wind-driven punch of a transitioning system raking across a coastline packed with tens of millions of people. Reports associated with the storm's approach to Japan included 24 or so injuries, with most in Okinawa and a couple in Kagoshima, dozens of houses partially damaged, flooding in areas near Tokyo, a partial collapse of a section of a national highway, water outages affecting roughly 1,800 households in one Tokyo suburb, and disruptions to rail lines. Mercifully, as Mekkhala raced toward the cooler water and rising wind shear of the higher latitudes, it began to weaken, dropping back from super typhoon strength to typhoon strength over the Philippine Sea by the morning of June 23rd, about 12 hours after its violent peak. The monster was already beginning to come apart, but the fact that it weakened on schedule should not lull anyone, because the lesson of this storm was never about its grand finale. It was about how fast it arrived in the first place. And that raises an obvious comparison, because this is not the first time this year the Pacific has produced something terrifying. To really measure Mekkhala, we have to put it next to the other monsters of 2026. The Philippine displacement deserves a closer look, because it shows how a storm can wound a country it never strikes head-on. The southwest monsoon, the habagat, is a seasonal flow of moist air the islands live with every year. What a passing typhoon does is supercharge it, acting like a pump that pulls that moisture in and wrings it out as torrential rain over the same regions for hours or days. The result is flooding and landslides far from the storm's center, which is how more than 85,000 people ended up displaced in Mindanao, while Mekkhala's eye stayed out over open water. A tropical cyclone's reach is far wider than the circle of its strongest winds. The steering that carried the storm onward is worth understanding too, because it will matter when we get to the theories people tell about why it went where it went. A subtropical ridge is a large dome of high pressure, and air flows clockwise around it in the northern hemisphere. A storm caught on the southern and western flank of such a ridge gets shoved along its edge, and as the ridge weakens or shifts, the storm curves with it. That is the marble on the rim of the bowl. And it is ordinary, predictable physics, the same mechanism that steers storm after storm along similar curving paths every season. Okinawa sits at a sensitive point on that curve, and not only because of its dense civilian population. The island hosts major United States military installations, and a powerful storm bearing down on a place like Kadena Air Base draws attention for reasons that go beyond the weather. Keep that in mind, because the storm's path toward a military base is going to come up again when we examine the claims that Mekkhala was aimed by human hands. For now, it is enough to know that the same steering currents guiding any storm along that arc were the ones carrying this one toward Japan. The transformation waiting for Mekkhala in the higher latitudes, the extratropical transition, is one of the most underappreciated hazards in all of tropical meteorology. People hear that a storm is weakening and assume the danger is passing, but a transitioning system can spread its damaging winds and heavy rain across a far larger area even as its tropical core falls apart. For a coastline as crowded as Japan's, and a metropolitan region as enormous as the one around Tokyo, a sprawling transition storm can be more disruptive over a wide area than a compact, intense one. The threat changes shape, but it does not simply vanish, and that is the reality the region had to prepare for as the storm raced north. To understand whether a storm is truly exceptional, you cannot look at it in isolation. You have to set it against its peers, and 2026 has already delivered some fearsome ones. Earlier in the year, the Western Pacific produced a super typhoon that reached Category 5 strength, the very top of the scale, a storm whose winds outran what Mekkhala managed at its peak. So if we are being scrupulously honest, and we always will be here, Mekkhala was not the strongest storm of the entire year by raw wind speed. That earlier Category 5 beast holds that particular crown. So why call Mekkhala the most violent storm of 2026 at all? Because the records it actually broke are about something more specific and, in a way, more meaningful than a single peak wind reading. Mekkhala is the most violent storm of this stretch of the season, and it is the strongest June typhoon in 22 years. The significance is in the calendar. A Category 5 in the heart of the season is frightening, but expected, the kind of thing the Western Pacific is built to produce when ocean heat is at its annual maximum. A storm of Mekkhala's ferocity in June, before the basin has fully loaded its guns, is a different kind of warning. It is the season arriving early and arriving angry, and that is precisely why this particular storm deserves the spotlight, even in a year that has already seen a Category 5. That earlier monster is worth remembering for another reason, because the most powerful tropical cyclones do something that most people never hear about. When a storm reaches truly extreme intensity, the energy it pumps into the atmosphere does not stop at the cloud tops we see on satellite. It can ripple upward, launching atmospheric gravity waves, vast undulations in the air that propagate all the way into the highest reaches of the atmosphere, into the layer called the mesosphere, near the very edge of space. Picture the ripples spreading out when you drop a stone into a still pond, except the pond is the atmosphere itself, and the stone is a storm the size of a country. That a weather system at the ocean's surface can send its signature to the doorstep of space tells you something about the sheer scale of power we are dealing with. It is also worth noting how rare the company is that Mekkhala now keeps. The strongest June typhoon in 22 years is, by definition, stronger than every June storm across more than 2 decades of an already busy basin, a stretch that includes some famously destructive years. To leap to the front of that line, a storm has to do something genuinely unusual, and Mekkhala did it by intensifying faster and earlier than the calendar should normally allow. That is the statistical fingerprint of an ocean that has more heat to give, and that is ready to give it sooner than it used to be. A single record can be chance. A record for raw intensity set weeks before the season's true peak is the kind of result that makes climate scientists look up from their screens, because it is exactly what the warming trend predicts. That power is the thread connecting everything we have talked about. The same heat engine physics that let Mekkhala double the rapid intensification threshold is the physics that lets the strongest storms reach toward space. The same warm ocean that fueled an 85,000-person displacement in the Philippines is the warm ocean that climate science says is being steadily warmed further. Every piece of this story points back to the same uncomfortable center, which is that the storms are getting a faster on-ramp and a higher ceiling, and the planet's warm oceans are the reason. When a storm is this dramatic and the stakes are this high, something predictable happens in the spaces where people gather online to make sense of frightening events. The explanations start to multiply, and not all of them stay tethered to the data. Some of them veer into territory that is worth taking seriously, not because the claims are true, but because the questions underneath them are real, and they deserve an honest answer rather than a dismissive one. So let us go there, into the theories, and let us weigh them carefully. The comparison with the season's earlier Category 5 storm is instructive in another way, because it shows how much the calendar shapes what counts as alarming. By the time the basin reaches the depths of its season, the ocean has banked an entire summer of heat, and the atmosphere has settled into patterns that favor strong storms. A monster in September is the system working as designed. A monster in June is the system jumping its own gun, reaching peak season ferocity before peak season has arrived. And that is the specific record Mekkhala set when it became the strongest June typhoon in 22 years. That is why anchoring the superlative to the calendar is not a dodge. It is the most truthful way to describe what makes this storm exceptional. It was not the single strongest storm of the year by wind, and we will always tell you that plainly. It was the most violent storm of this part of the year, the strongest June typhoon in over 2 decades, an out-of-season heavyweight in a year that was already producing heavyweights. The early arrival is the warning, and the warning is more meaningful than any single wind reading. The reach of these storms into the upper atmosphere is worth dwelling on for a moment longer, because it captures the scale of the energy involved better than any wind number can. When the most intense tropical cyclones pump heat into the sky, the disturbance does not stop at the cloud tops. It launches waves that travel upward through layer after layer of the atmosphere, all the way to the mesosphere near the boundary with space. A storm sitting on the surface of the ocean can leave its fingerprint at the doorstep of the sky. That is the kind of power we are talking about, and it is the same power that warming oceans are learning to summon faster and earlier. Every one of these threads ties back to the same center. The physics that let Mekkhala double the rapid intensification threshold, the warm sea that fueled a displacement of tens of thousands, the reach into the upper atmosphere, the out-of-season record. They are all expressions of one fact, which is that a warming ocean gives storms a faster fuse and a higher ceiling. And it is precisely because that fact is so unsettling that people reach for other explanations, ones that feel more controllable than the temperature of the entire sea. Those explanations deserve a fair and careful hearing so that we can see clearly where they go wrong. Whenever a storm explodes the way Mekkhala did, a certain set of explanations reliably surfaces, and the most persistent of them is the idea that the storm was not natural at all, that it was engineered or steered by some human hand. Often the accused is a facility called HAARP, the High Frequency Research Program in Alaska, that has become a kind of all-purpose villain for weather conspiracy theories. The claim takes on extra force when people notice that Mekkhala's forecast path carried it toward Kadena Air Base, a major United States military installation on Okinawa, which to some looks less like coincidence and more like a target being painted. I want to take that seriously, so let us actually do the math, because the math is decisive. A mature typhoon releases energy at a staggering rate, on the order of hundreds of terawatts, when you account for the heat it processes as it condenses water vapor across its enormous structure. That is a sizable fraction of all the sunlight striking the entire tropical band of the planet, and the total energy a large storm handles over its life dwarfs all of human electricity generation by many orders of magnitude. Set that against any transmitter or facility human beings have ever built, and the gap is not close. It is a chasm of factors of millions. There is simply no installation on Earth that commands a meaningful fraction of the power a typhoon wields, which means no facility could create one, and none could steer one. And the apparent targeting of Kadena? That has a thoroughly ordinary explanation, and you already learned it earlier in this very story. Mekkhala was riding the edge of a subtropical ridge, that dome of high pressure to its northeast, the way a marble rolls around the rim of a bowl. The rim led toward Okinawa. The storm followed the steering currents that the atmosphere laid down, the same currents that guide countless storms along similar arcs every single year. A path that looks deliberate when you stare at a single map is just physics when you understand what is pushing the storm along. Then there is the second theory, the one that says the authorities are hiding the storm's true strength, or alternatively, that they are exaggerating it to frighten us. And here is where that detail from the beginning of the story comes back, the one I asked you to hold on to. Remember that Mekkhala carried 3 different names, and remember that different agencies measure it differently. The Joint Typhoon Warning Center reports winds averaged over 1 minute, while the Japan Meteorological Agency uses a 10-minute average, and a 10-minute average of the same wind will always produce a lower number than a 1-minute average. So you can look at 2 official sources, see 2 different wind speeds for the identical storm, and conclude that someone is lying. But nobody is lying. You are simply looking at 2 rulers with different markings measuring the same thing. What looks like a cover-up or like hype, is usually just the unglamorous reality of competing measurement standards. The third theory is the most interesting because it contains a genuine kernel of truth, and I would be doing you a disservice to wave it away. The claim is that Mekkhalla's intensification was unnatural, that no storm should be able to strengthen that fast on its own. And you know what? The instinct behind that is not wrong. Rapid intensification of this magnitude is genuinely alarming, and it is genuinely becoming more common. The mistake is in the cause. It is not a secret machine. It is the warming ocean, an effect that is measurable, predictable from basic physics, and consistent with the broader trend we walked through earlier. The truth is more unsettling than the conspiracy, because a secret weapon could, in principle, be switched off. A warming ocean cannot be, not on any timescale that helps us soon. The disturbing answer was never being hidden from you. It was sitting in plain sight the whole time, in the temperature of the sea. It is worth asking why these theories take hold at all, because the answer is not that people are foolish. The answer is that a storm exploding from nothing into a monster in a day and a half feels like it must have a hand behind it. The human mind is built to find agency, to look at something frightening and sudden and ask who did this. And a faceless warming ocean is a deeply unsatisfying culprit. A secret machine, by contrast, gives the fear a target and a name. So the impulse behind the theories is understandable, even sympathetic. It is the conclusions that do not survive contact with the evidence. There is also a real grievance buried inside the suspicion, and it deserves acknowledgement rather than dismissal. When people sense that something is being kept from them, they are sometimes responding to a genuine gap, just not the one they imagine. The honest failure around storms like Mekkhala is not a cover-up of the data, which is public, updated constantly, and available to anyone who looks. The failure, where it exists, is one of preparation and of framing, of communities and infrastructure left more exposed than they should be, and of a public that is rarely told plainly how the odds are shifting. That is a real problem, and it is a structural one, not a secret. So when the data is sitting in the open and the mechanism is understood, the most radical thing you can do is simply look at it clearly. The ocean is warm. It is getting warmer. Storms that feed on warm water are gaining a faster fuse. None of that is hidden, and none of it requires a villain. It only requires us to be willing to accept an answer more uncomfortable than a conspiracy, because a conspiracy could be exposed and stopped, while a warming ocean asks something much harder of us. That brings us back, in the end, to the storm itself, fading now over cold northern water, and to the single most important thing it has to teach. Because the lesson of Mekkhala was never about the wind, or the eye, or even the places it threatened. It was about what its speed reveals, and about a future that is already arriving faster than our warnings can keep up with. When the satellites finally lose track of Mekkhala somewhere in the cold North Pacific, when the warnings are canceled and the ports reopen and the news moves on, it would be easy to file this storm away as another near miss, another monster that mostly stayed over open water. That reading would miss the entire point. Mekkhala did not flatten a great city. What it did was demonstrate in June with brutal clarity how quickly a modern Pacific storm can convert a warm ocean into a Category 4 weapon, and how little time that leaves for the islands and coastlines in its path to react. The story of this storm was never really about the damage, as real as that damage was for 85,000 displaced people in the Philippines, and for the communities bracing across Okinawa and Japan. The story was about speed and about timing. It was about a storm that nearly doubled the threshold for rapid intensification, that reached the doorstep of super typhoon status in a day and a half, and that did all of it a full season ahead of schedule. Every one of those facts points in the same direction, toward an ocean that is handing storms a faster fuse and a bigger payload, And that is what turns a distant typhoon into something that should matter to you, wherever you live, whether or not you will ever see a tropical cyclone with your own eyes. Because the lesson of Mekkhala is not confined to the Western Pacific. It is a preview of a pattern that is showing up in warm oceans all over the world, from the Atlantic to the Gulf to the Bay of Bengal. The pattern is this: the season starts earlier, the storms ramp faster, and the warning, the precious lead time that all of our preparation quietly assumes, gets shorter with every fraction of a degree we add to the sea. It is tempting, too, to assume that because the forecasts track this storm so well, we are fundamentally in control of the threat. The track forecasts were indeed good, and that is a real achievement worth celebrating, the product of decades of patient science and better satellites and faster computers. But knowing where a storm will go is only half of safety. The other half is knowing how strong it will be when it gets there. And that is the half rapid intensification keeps stealing from us. A flawless track forecast attached to an intensity that doubles overnight still leaves a community preparing for the wrong storm, bracing for a tropical storm, while a Category 4 bears down. That is the piece of the problem that warming oceans are quietly making worse, 1 degree at a time. There is a strange comfort people reach for when a dangerous storm weakens before it can do its worst. A sense that the system worked, that we dodged it, that the models held. But dodging a bullet is not the same as being safe, and a storm that weakens on its way to Tokyo does nothing to change the ocean it was born from. That ocean is still warm. It is getting warmer, and it is still out there, ready to do the same thing again, perhaps next time over water with a coastline directly downwind, perhaps next time with no friendly patch of cold sea waiting to take the edge off before landfall. So here's the question I want to leave you with, the one that lingers long after Mekkhala is gone. We have always told ourselves that we would see the big one coming, that the warning would arrive in time, that the gap between danger and disaster would hold. But what happens to that promise when the storms learn to sprint? What happens when the fuse keeps getting shorter, and the ocean keeps getting hotter, and the next monster forms not in the heart of the season, but a season early, the way this one did? Mekkhala is fading now, a swirl of cloud unraveling over cold water. The warning it carried is not fading at all. It is rising, quietly, in the temperature of every ocean on Earth, and it is waiting for the next time the dice come up violent.